So, a few months ago, I started to wonder, what if I could introduce disease into a large language model just by changing some of the parameters? Would it produce neurological symptoms similar to what you may find in patients? For example, could I simulate a degenerative disease like dementia just by updating some of the weights? So here's the plan. I'm going to install a small model on my Mac Studio, then write some code to randomly damage the parameters and see what happens. Let's start with the hardware. I'll be using a Mac Studio with an M4 chip and 128 gigabytes of RAM. But since I'm using a small model for this experiment, you could probably get away with 16 gigabytes of memory as a less expensive option. The model I'll be using is called Qwen 2.5 Coder 14B, and it's about 8 gigabytes in size. Before I start breaking the model, let's see how it performs under normal conditions. This will be the control in my experiment. For all my tests, I'll use the same prompts. I'll ask it to write a poem about the city of Detroit. Okay, that looks like a poem to me. So, throughout the video, I'll be using this response as a comparison to see how things are changing. Okay, this is going to be a pretty technical video, so I'm assuming you already know how a large language model works. And more specifically, you should have a high-level understanding of the different layers. For example, the embedding layer and transformer blocks, which includes the self-attention and feed-forward networks. And finally, the language model head. If you need a refresher, check out my last video about understanding AI. I'll have a link to the video in the description below. So this is a conceptual diagram of a model, but next I want to show you the actual files used by an LLM. Let's go to Hugging Face and take a look at the structure. Here's that Qwen model that I'll be using, and if you click the Files and Versions tab, you can see all the files that make up the model. For this video, I'll focus on 4 of the files. The first one is config.json, which gives an overview of the model. One section I want to highlight is the quantization block here. See how it says 4 bits? That'll be important in a few minutes. But for now, let's get back to the files. Here we have 2 Safetensor files, and these files contain all the trained parameters and make up the bulk of the model. For this video, you can think of a tensor as a multidimensional array. Finally, we have an index file for the Safetensors. This is pretty important because it shows all the different layers that make up a model. At the top of the file, you can see a language model head, which is the last layer in the model, and the embedding layer that we talked about earlier. There are also a large number of transformer blocks, 47 for this particular model. And the transformer blocks are split between self-attention and MLP layers. MLP stands for multi-layer perceptrons, and this is the same thing as the feed-forward network. There is one type of tensor that deserves a little more attention. See all these scales entries? These are used for quantization, where quantization is a way of reducing the memory footprint of a model. Now, quantization is a big topic, but for now you can think of it as a way of storing floating point numbers as integers. This can reduce the model size by a factor of 2 to 4, depending upon the quantization method that's used. Okay, now that we understand how the models are structured and organized, it's time to write some code to modify the values. To generate the code, I used a different model called Qwen 3.5 35B. With the prompt, I was able to create a Python script that can update parameters by layer. And I gotta say, for a small model, I'm kind of impressed. It took a few passes to get the code completely working, but it did a pretty good job. Now it's time for the fun part. Let's start to break the model. First, I'll back up the original Safetensor files, then I'll start with the embedding layer. And again, that's the first layer in the model that converts tokens into a long list of numbers called embeddings. So my guess is this is going to absolutely wreck the model. I mean, this is the entry point that establishes all the relationships for a token, but let's see what happens. Running the script, you can see some of the weights and how they've changed. And just as predicted, the results are pretty bad. I mean, it looks like it's just returning the letter W. Okay, I decided to dial a few things back and reduce the number of weights that were updated, which is producing better results. It's kind of interesting. It seems like it's generating less words. My guess is, so here's my guess. It seems like since the embeddings are broken, maybe the self-attention layer is struggling to find a match, causing it to prematurely select the end of sequence. But at this point, I'm just not sure. Oh, by the way, one important thing I forgot to mention. For each one of these runs, I'm completely clearing out the context and restoring the original tensors, just to give it a clean slate. Okay, time to open up the transformer block. And I'm going to start with the self-attention layer, and specifically the Q tensors. You can think of this as the mechanism where a token poses a question to other tokens looking for a match. I have no idea what's going to happen here, so let's update the tensors and see what we get. This is, it's kind of interesting. It seems like it's having some trouble demarcating the tokens. Like, it can't figure out where a space should be in some of the words. Also, again, it looks like we have less output than our control. Okay, let's continue. The next layer is the most interesting to me. It's called the feed-forward network, or multi-layer perceptron, or MLP. In my last video, I explained how this layer narrows things down and kind of acts as a knowledge repository for the model. Approximately 2/3 of a model is made up of these layers. The most interesting aspect to me is what comes out of these neurons is something like fragments of thought instead of concrete things like deciding between pizza or salad. And this is kind of sort of the way our brains work, where thoughts or ideas are clusters of neural activations. Okay, I'm really hoping for some interesting results, so let's see what happens. Okay, I'm not too sure what to make of this. I think I'm going to do a few more runs. And just to mix things up, I'll also generate some code here, since we're getting some interesting results. So the code had a few issues, but it wasn't too bad, and it definitely was better than I was expecting. Now I'm going to try to break two feed-forward networks in different layers. I'll try layers 33 and 40, and these are towards the back end of the model. The results are, I guess, a cross between a lucid dream and just some flat-out hallucinations. It's pretty interesting though, and yeah, let's keep going. Yeah, this is interesting. Okay, finally, let's try the language model head. This is where the original embeddings have transformed throughout the model, and we're ready to predict the next token. I'm going to take a guess and say this is going to completely break the model, but let's see what happens. And just as expected, this is this is just gibberish, but yeah, let me try again. And, you know, it's kind of interesting that it's falling back to Chinese and Unicode characters. This is a Chinese model, so I guess it kind of makes sense. Okay, that was pretty cool. If you're interested in trying this out for yourself, I'll have all the code and instructions in my GitHub page, linked in the description below. And again, thanks for stopping by, and I'll see you in the next video.